Friends, welcome to lecture number 50. This is mostly on the tutorials. So, we are going to work on some of the problems dealing with the drainage, subsurface drainage using Hoogout equation and Glover-Dunn equation, and finding out the drain spacing and finding out the drain pipe length, pipe diameter and all those things. Okay. So, here in example 1, if you see, so it is a tile drainage problem. So, the tile drains have to be installed in an agricultural land having soil permeability of 2.3 into 10 power minus 3 mm per second. So, that is your hydraulic conductivity, and impermeable stratum exists 3.2 below the land surface. Okay, and it is designed to keep the water level at least 1 meter below the land surface. So, this is what we are expecting from the drainage system. So, that means the root zone we are expecting 1 meter below the soil surface. The average discharge of the drainage system is 2 mm per day. Okay, so, if the tile drains are planned to be placed at 1.5 meter below the land surface, so the drain spacing, so assuming the equivalent depth to be same as the tail depth. So, what would be the drain spacing? So, that is the problem here. So, from the given data, so the K is given 2.3 into 10 power minus 3 mm per second, that is the K for this stratum, and impermeable layer, that is 3.2 meter from the surface here, and these are the two tail drains. Okay. And then we are expecting 1 meter below the soil surface the water table, okay, in a day, and the drain base depth, so that is 1.5 meter from the surface. Okay. And then here the other information is given, like the drain, we are giving the Q is equal to 2 mm per day. So, this is we are expecting from the drains, tail drains. So, in this case, what would be the spacing? Okay. So, that is the problem here. Okay. So, given K is given, right, Q is given, like equivalent depth, here the equivalent depth is same as the tail depth, that is 1.5 meter. Small h is equal to 0.5, because this is 1.5 minus 1. So, this is small h, this is W minus capital H, right, that is a small h, that is 0.5. So, then so the next thing is, so the Hoogout equation in both the drainage flow above the drainage base and below the drainage base, if you consider. So, this portion will give the drainage flow contribution above the drain, and this below the drain, and this is above the drain. Okay. So, substituting the values of Hoogout equation, now the values are given already, K, D is given, H is given, right. So, then so Q also given. So, simple substituting the given parameter values. So, you get L is equal to 26.37 meters. Okay. So, this is a direct formula based problem, right. So, the parameters, all parameters are given, the only thing is to find out the spacing in that case. Okay. So, the next problem here, in an irrigation command area, the irrigation interval, okay, so the gross application in an irrigation and the application efficiencies are 20 days, that is irrigation interval, 75 mm, that is gross application, right, and 60% is the application efficiency. So, the soil is homogeneous and K is equal to 0.9 meter per day, that is the hydraulic conductivity. The impermeable layer is at a depth of 7 meter from the ground surface. Okay. So, like there is an impermeable layer from the ground surface. So, this is about 7 meter, the area to be tile drained with tiles at a depth of 2 meter below the ground surface. So, there are at a 2 meter, right. So, you have the tiles installed. The maximum permissible steady state water table height midway between the drains. So, here, so this one is from the plane of the drain is 1.2 meter, right, water table height. So, this is 1.2 meter. Using the steady state approach of the Hoogout, assuming an equivalent depth of 4.12, the drain spacing. So, equivalent depth, so this will be 4.12 meter. So, the drain spacing will be how much? So, what would be the drain spacing? Okay. So, here also the drain spacing formula, if you see small q, which is equal to, right, 8 k d h divided by L square plus 4 k h square by L square, right. So, the values are here. So, h you can find out like 2 minus 1.2, you get small h. So, that is fine, and d equivalent depth is given 1 point and k is given, right. So, the other thing, the spacing needs to be find out, and you have to estimate the q. So, this is very important. So, otherwise all parameters are given. So, this value will be estimated using the data given like 20 days, 75 and 60%. So, from that you are going to estimate, then once you know q value, you can estimate the spacing. So, let us see how can be solved. So, here the given irrigation interval is given, gross application irrigation, that 75 mm, application efficiency is 60%. So, therefore, small q is equal to 75 divided by 20 days irrigation interval. So, we will be knowing the daily water requirement, gross requirements, that is 75 by 20, that is 0.6 is the efficiency term. So, you get 2.25 mm per day, and if you can convert that in a meter per day. So, this 0.00225 meter per day, and k is given, right. So, then the other data like 7 meter and 2 meter is the drainage depth. So, h is equal to 1.2, because so here so sorry, here now down, this is not 1.5. So, this is h is equal to 1.5. Okay. So, the small h is equal to, so 2 minus 1. Sorry, 2 minus 1.5, you will get 0.5. So, you are supposed to get points. Let me see the values, right. Let me see what is capital H. So, the capital H value here it is 1.2, right, 1.2. So, this will be so H is equal to this will be 1.2, right, capital H is equal to 1.2. So, 2 minus 1.2, so capital H is equal to 1.2. So, the 2 minus 1.2 we will give the 0.8, right. So, 0.8 is a small h. Okay. So, and d is 4.12. Now, if you can substitute the values here, sorry. So, if you substitute these values in this equation, okay. So, the q is given, so all parameter values are known, right. So, substituting the values, so L value will be 134.63 meters. Okay. So, this is almost similar to the previous equation, sorry, previous problem. Only thing is q needs to be determined based on the irrigation efficiency, gross water requirement, right, and also the irrigation interval. Okay. And then example 3 here. So, this is a leachate requirement problem. So, the EC of the canal water used for irrigation irrigating wheat crop is 1.2 millimoles per centimeter. So, this is the electrical conductivity of the irrigation water, while it can tolerate a maximum EC of 6 millimoles per centimeter. This is regarding the soil. So, then ET of VT is 0.8 centimeter per day and the soil hydraulic conductivity 0.9 centimeter per hour. The area is to be drained by the tail drain laid at 2.5 meter below the ground level. So, the tails are laid at 2.5 meter below the ground, okay, and maintain water tables at 1.5 meter. The impervious layer is located at a depth of 1.4 meter. So, if this is impervious layer, so this is about 4 meter below the ground surface and the area and 2.5 meter below the ground level, below the ground level. Okay. So, as to maintain the water table depth at 1.5 meter, okay, water table depth at 1.5 meter, okay, and the impervious layer is located 4 meter below the ground surface. So, compute the drain spacing using Hoogout equation. So, what would be the drain spacing and calculate the drainage flow out of 400 hectare field. So, then Q, what is Q from 400 hectare field and what is the size of drain pipe laid out in a gradient of 0.001 meter per meter, assuring that drain is running full and Manning's N is 0.01. So, this is the Manning's N. So, that is 0.01. So, in this problem, so the first thing is you need to find out what is irrigation, leachate requirement using the EC values of water as well as the crop tolerance level. Okay. So, with this knowing the leaching requirement, now you have to find out the irrigation requirement. Okay. So, then from there you will be finding out what is Q. Okay. So, that is the first question and the next this is so knowing Q value. So, you can find out L. Okay. Then drainage flow rate for 400 hectare field can be estimated and then knowing the Q, right, knowing the Q and Manning's equation. So, you can find out the diameter of the pipe or the tail pipe. Okay. So, now the given values are here EC IW irrigation water, EC DW that is drainage water, that is 6 millimoles per centimeter, and then with this we are going to find out the leachate requirement. So, ET is given 0.8 centimeter per day, soil hydraulic conductivity 0.9 centimeter per hour, tail drain depth is 2.5 meter, water table 1.5 meter and impervious layer 4 meter and area 400 hectares, gradient, that is a slope 0.01 meter per meter and then Manning's roughness coefficient, that is N, which is equal to 0.01. So, we know the leachate requirement formula LR is equal to EC IW by EC DW. So, substituting the values here EC IW 1.2 and EC DW 6. So, you get leachate requirement is 0.2 and so using this leachate requirement. So, you are going to find out the depth of water drained. So, that will be the depth of water applied minus depth of irrigation requirement. Okay. So, or in other words, depth of water applied is equal to depth of water for irrigation and depth of water for drainage, that is for leachate requirement. Okay. So, the depth of water drained is equal to, so irrigation depth minus leachate requirement into irrigation depth. Okay. This is extra amount you need to apply as irrigation, so that the salts can be leached out. Okay. So, the DI minus leachate requirement 0.2 and DI. So, the total will be 0.8 DI. So, and this will be equivalent to depth of water drained. So, we are equating that to 0.8 DI, right. We are expecting if that much drained water is taken by the crop, right. So, ET is here the drainage water, okay, because that much water is taken up by the plants. So, then substituting these values d I is equal to 1 and leachate requirement is d d minus d I, and d d the drainage depth will be 0.2 into 1, that is 0.2 centimeter per day. Okay. So, this is in a day. See, drainage flow rate is equal to 0.2 centimeter per day, and now using Hoogout equation. So, this is contribution of drainage water just above the drain flow, above the drain base depth and below the drain base depth. Okay. And then so all values are known except L. So, you can easily find out the value of spacing, like substituting the values you get 41.47 meters, and drainage flow rate Q is equal to small q multiplied by capital area, I mean A, that is area. So, that will be 0.2 by 100 because this is unit conversion, and 400, that is hectares, and again you convert into meter square. So, the total will be now 8,000 meter cube per day of drainage water, which is resulting from the area 400 hectares, and you can convert 0.092 meter cube per second. So, and then now Q is equal to A into V. So, this is to estimate the diameter of the tail pipe, okay, or the tile pipe. Q is equal to A into V. So, V is equal to 1 by N. This is a Manning's roughness equation. So, Manning's equation, if you substitute for V, then Q is equal to A into this is the velocity. Okay. So, Q is equal to, so A can be substituted as pi by 4 d square into 1 by N. So, and R pi d square by 4 pi d, right. So, because R is equal to A by P, since it is a circular. So, this is pi d squared by 4 into perimeter. So, that is so perimeter is pi d. So, you get the pi d square by 4 pi d. Okay. And substituting the values here for Q and for other values, you end up with now d is the unknown parameter. So, now finding out the d, you get 41.1 centimeter. So, that is the diameter of the pipe which can accommodate the drainage flow rate. Okay. And then this is example number 4. So, here the following data were obtained from an agricultural land requiring a pipe drainage system for groundwater control. Okay. So, hydraulic conductivity is given 8.3 centimeter per hour, drainable porosity, that is a 5%, reaction factor, that is alpha we discussed, that 0.31 per day, and equivalent depth through the impermeable layer, that is DE 2.8 meter. So, the drain spacing computed by Glover-Derm formula will be, so that we need to find out what would be the drain spacing from Glover-Derm equation. So, you remember the Glover-Derm equation for unsteady state flow we used. So, hydraulic conductivity is given 8.3 centimeter per hour. So, that is 1.992 meter per day, and drainable porosity is a 5%, reaction factor alpha which is 0.31 per day, and equivalent depth through the impermeable layer, that is 2.8 meter. So, with this data and from Glover-Derm equation you get L square is equal to, this is a simple Glover-Derm equation, 10 k d by mu alpha, and L square is equal to 10, k is given, d equivalent depth is given, and mu and alpha is given. Okay, this is the 5%. Now, L square, so this is the drainable porosity, right, and this one is the reaction factor. So, now L is equal to 59.98 or 60 meter, that is a spacing. Okay. And then So, in the next example, this is a subsurface drainage system, right, installed in an agricultural area to control the water table. So, that is the purpose, and the design discharge rate of the drain is 2 mm per day, that is small q, and the depth of water table midway between the drains is 1.5 meter below the soil surface. So, that you have this is the drain base depth, okay, and this is impervious layer, right. So, we are expecting here exactly. So, in the midway between the drains, so the depth of water table we are expecting is 1.5 meter, this one, right, and q from here, the q is equal to 2 mm per day, 2 mm per day, okay. And drain pipe with radius of 0.1 meter is installed at a depth of 2 meter. So, this is installed at a depth of 2 meter. There is an impervious layer. So, impervious layer is 7 meter. Then hydraulic conductivity of the homogeneous soil above the impervious layer is 1 meter per day. So, the K which is equal to 1 meter per day. Okay. So, the questions here are, so if the flow rate takes place only below the drain level, the equivalent depth for drain spacing of 90 meter is. So, what would be the below the level, the equivalent depth for, what is the equivalent depth? So, what is dE? You have to estimate. So, this is the, you have to find out what is dE, and then if the flow rate water takes place only above the drain level, the drain spacing is. Okay. So, it is like in both cases you are going to find out what would be the drain spacing as well as the dE. Okay. So, let us see this. The values given, the discharge rate of the drain small q, which is 2 mm per day, hydraulic conductivity 1 meter per day, and we are going to list out the other known parameters. Okay. So, the first thing is, so here this is 7 meter below, as I mentioned 2 meter is a drain base depth, and 1.5 meter we are expecting from, I mean, the water table to be down at 1.5 meter below the ground. Okay. So, all right, and then as we know Hoogout equation for water. So, this is equation of water flow or water contribution or drainage contribution above the drain base depth. So, that is L square is equal to 8 d k h by q, and so 90 L is given, right. Only thing is d is you need to calculate. So, from this, so d can be estimated as okay. So, from here, so d can be estimated as 4.05 meter, and the above drain level. So, this is the equation, L square is equal to 4 k into h square by q. So, substituting the values here, you get L is equal to 23.36 meters. Okay. So, here in this example, so we found out the contribution, if you know the contribution of q above the drain base depth and below the drain base depth. So, you can find out the corresponding, the drain spacing as well as the depth to, I mean, from the impervious layer to or equivalent depth, okay, from impervious layer to drain base depth. Okay. So, this is all the tutorial. So, in this basically we were talking about the steady state problems as well as one problem on unsteady state problem using Glover-Dunn equation. Otherwise, most of the problems are related to the Hoogout equation, and we have seen the variety of equations finding out spacing, finding out the drain flow rate, okay, and contributions of flow above and below the drain base depth. Okay. So, I mean, I think this variety of problems definitely will help in understanding the problems, right, related to surface as well as subsurface drainage systems design. Okay. Thank you so much.